Continue today to talk about mathematical induction, not to be confused with its physics concept of self-induction, where we talk about potential differences and fluxes, but this is mathematical induction, which is a method of proof. I'm not sure how many of you guys are familiar with these domino rally sets, which existed well before you were born and will date your teacher. As you can tell that he's really, really old now. But let's see if we have some old video. The internet decides to cooperate with us. If it does, great. If it doesn't, oh well. But I kind of wanted to give you an idea of what we're talking about today. With this principle. Okay, it's not cooperating. Screw it. Taking too long. But the idea with mathematical induction is that we're trying to create a chain reaction. So, with that in mind, let's speak to the point of our objectives for today. Oops, too fast. Back. So our first objective is to use mathematical induction to prove a statement. The second is how to find the sums of powers of integers. The third is to recognize patterns and to write them in terms of an end of a sequence. And the last is to find finite differences of a sequence. Okay. So in mathematical induction, as I've mentioned before, the idea is kind of a chain reaction. We're trying to show something to be the case. We show it for one, then we assume it for another, and then afterwards we try to prove it for the last half of it. So we have two forms of induction, or mathematical induction. We have weak form and strong form of induction. Okay, the weak form is where we verify the first term, we assume k to be true, and we show it for k plus 1. The strong form is where we verify for k, and we prove it. This verification implies it for k plus 1, and we'll talk more about that in detail later. Okay. So let's open up the box and give you an idea of what we're talking about. Okay. So the principle of mathematical induction we have three pieces. We have kind of three pieces to the puzzle. We at S of n. Don't confuse this for the sum. This is a statement symbol. Okay. Your book uses P of n. That's okay. So does let S of n or P of n be a statement involving the positive integer n. This is our weak form. Okay. Okay. If S of 1 or P of 1 is true, and the truth of S sub k implies the truth of k plus 1, then S of n is true by mathematical induction. Okay, so it sounds really complicated, but it's actually not that painful. So we need to be able to apply it to a statement of k plus 1. So before we even actually do mathematical induction, let's do a couple of examples of plugging in k plus 1 for our problem here. So example 1, find pk plus 1 for each pk with a and I'll just do one more. Okay. Alright, so when we plug in k plus 1, what we do is we plug in k plus 1 wherever we see k. Okay. So for solution A, we have p is equal to k cubed, so a plus 1 over 5. Wherever I see k, I put in k plus 1. Okay. So I see k in two spots here. Let's use orange for that, or red. Actually, yeah, orange. Okay. So wherever I see k, I put in k plus 1. So k plus 1 cubed times k plus 1 plus 1 over 5. Okay. So we don't need to expand it. We can just leave it as is. And then that becomes k plus 2 all over 5. The same thing for letter B. And for letter B, we have 2k times 2 squared, k squared. For letter D, right, wherever I see k, once again, I put k plus 1. Oops. K plus 1 squared. And that's going to be our p of k plus 1. Okay, so you got the idea here. We simply replace the k with k plus 1 and we simplify it. Okay. And now that we've kind of have this idea, let me have you do one on your own without guidance. Then we'll come back and we'll talk about mathematical induction, the formal process of it. Okay. P Okay. Alright, so I'll have you do this example, and then after that we'll come back and we'll talk about mathematical induction.